Welcome to another module in this massive open online course. So we are looking at the average code length for a code, and we have shown a fundamental bound wherein the average code length is lower bounded by the entropy of the source. So the average code length, so the entropy of the source is the lowest possible average code length of any prefix free code that can be designed for a given source. Okay. Now let us look at what are the optimal code word lengths which can be used to approach this minimum possible average code length. Alright. So in this module what we would like to look at is we would like to address the question of what are the optimal, if I were to design such an code with minimum average code length, minimum average code length, what are the optimal code lengths? Alright, and the idea is basically in order to approach approach lower bound, which is of course we have seen is given by the entropy Hx of the source. Okay. So we want to find the optimal set of lengths. Optimal set of code word lengths L0, L1, M1. Of course, now since we are designing a prefix free code, remember this has to satisfy the Kraft inequality. These code word lengths have to satisfy Kraft inequality, that is summation I equal to 0 to m minus 1 2 to the power of minus Li has to be less than or equal to 1. So we can formulate this to find the optimal code word lengths. We can formulate this as an optimization problem, right? We want to find the optimal value of any function. We can formulate it as an optimal. Here, the optimization, we would like to optimize the code word length. In particular, we would like to minimize this average code length. Alright, so we can formulate this as an optimization problem subject to this constraint. There is a constraint. Remember, any such prefix, the lengths of any such prefix free code design have to satisfy the Kraft inequality. So the Kraft inequality acts as a constraint. Alright, so therefore we will have a constrained optimization problem for minimizing the average code length. Alright, so we can formulate this as a constrained Okay, so that is the key word here, that is this is a constrained optimization problem. And what is the optimization problem? The optimization problem is specifically minimize the average code length, which is summation I equal to 0 to m minus 1 pi Li, subject to the constraint which is the Kraft inequality, I equal to 0 to m minus 1 2 to the power of minus Li less than or equal to 1. This is known as the objective of the optimization problem. This is known as the objective. This is known as the constraint. Okay. And now what we can do is, this is a constraint optimization problem. So we can use the Lagrange we can use the Lagrange multiplier framework. Okay, the Lagrange multiplier framework is also known as the KKT framework, the Karush-Kuhn-Tucker framework to solve a constrained optimization problem, which basically uses a Lagrange multiplier. Okay, so basically we can use a Lagrange multiplier. Let's put it this way, you can say rather than a Lagrange multiplier, we can use a Lagrange multiplier framework to solve the optimization problem above. And what is the Lagrange multiplier framework? We form a Lagrangian with the objective. You must be familiar with this from a basic course on mathematics or even an advanced course on optimization. So, I form the Lagrangian which comprises of the objective summation pi li plus lambda times the constraint summation I equal to 0 to m minus 1 2 to the power of minus li minus 1. Now, this lambda, this is known as the Lagrange multiplier, the Lagrange multiplier. The Lagrange, the lambda is known as the this is known as the Lagrange multiplier. Now, what I am going to do? I am going to differentiate with respect to each pi. Okay, so what we are going to employ is from the KKT framework, the Karush-Kuhn-Tucker framework. What we do is the differentiate. This we have formed the Lagrangian, which comprises of the objective plus lambda, which is a Lagrange multiplier, times the constraint. Okay, remember this is your constraint. You have to have one Lagrange multiplier for each constraint. We have only one constraint, so we have a single Lagrange multiplier, and now we are differentiating with respect to each pi and set equal to 0. I differentiate with respect to each pi and set equal to 0. Now, when you differentiate with respect to pi, of course, you can say summation pi li. If you differentiate with respect to pi, you get li plus. Now, when you differentiate lambda summation 2 to the power of minus li, that picks 2 to the power of minus li. Of course, if you differentiate any other 2 to the power of minus lj with respect to li, that derivative is 0. Similarly, if you differentiate any other pj lj with respect to li, the derivative is 0. So, you are picking that particular I when you are differentiating with respect to li plus lambda times derivative of 2 to the power of minus li is 2 to the power of minus li into derivative of minus li, which is 1 times log that is log 2 to the base e, that is basically ln2, log natural 2, that is basically the natural logarithm of 2, and this must be equal to 0. I am sorry, when you differentiate pi li, this is simply pi. Differentiate pi li with respect to li, this is equal to pi. So, this is equal to 0, which implies that, of course, if you differentiate here lambda into minus 1 minus lambda with respect to li, that derivative is 0, because lambda is a Lagrange multiplier, differentiating with respect to li, that derivative is 0. Okay. So, we have this equation over here. Now, you solve this to obtain pi. So, what we have is basically 2 to the power of minus li. If you look at that, that is equal to, well, or 2 to the power of minus li is equal to pi divided by lambda log natural 2, which implies li equals log to the base 2 of lambda ln2 divided by pi. Okay, that is easy to show. Okay, so this is the optimal average length. Now solving this Lagrangian, setting the derivative, differentiating with respect to pi, setting equal to 0, we have obtained the optimal code word length, not average length, optimal but of course we have to find the Lagrange multiplier, we still have to find the Lagrange multiplier lambda. Still have to find lambda, and we find lambda from the constraint. To find lambda, we use the constraint, that is summation I equal to 0 to m minus 1 2 to the power of minus li is equal to 1. Remember, this is the Kraft inequality, this is a constraint which is satisfied with equality if we have a positive Lagrange multiplier. And now you substitute this value of li, which is summation I equal to 0 to m minus 1 2 to the power of minus, of course li I substitute from, let us call this equation as hash. So substitute, so in this substitute li from equation hash, so that will be 2 to the power of minus log to the base 2 lambda ln2 divided by pi is equal to 1. Now 2 to the power of minus log to the base 2 lambda ln2 divided pi, this is nothing but summation I equal to 0 to m minus 1, this quantity is pi divided by lambda ln2, which is equal to 1. Now we know summation pi is equal to 1, this implies simply that lambda ln2 is equal to 1. Okay, so that is the equality that we have using the constraint, and therefore this finally substituting the value of this lambda ln2, the optimal length which we can call as li star equals log to the base 2 lambda ln2, which is 1 divided by pi. So optimal code word length, and this is interesting, the optimal code word length, what we have thus derived is the optimal code word length, that is optimal code word length which minimizes the average code length. And observe that li star equals log 2 to the base 1 over pi, this is inversely proportional, look at this. So this is inversely proportional to pi, which means the larger the probability, that is symbols which have a larger probability have to be represented with lower and lower code word lengths, because they occur more frequently. An efficient representation would be to represent them using code words which have lower length. So the largest probability symbol naturally has to have the lowest code word length for efficiency. And that's what this optimal length, that's what this the optimal length that we have derived using this paradigm, that is the Lagrange multiplier, using the the Lagrangian, that is a KKT framework, using by solving this constraint optimization problem, the optimal lengths that we have derived, code word lengths that we have derived, reflect this very fact. Okay. So, this implies larger probability. So, this says that larger probability implies larger probability implies lower covert. Okay. This is for efficient representation. This is for towards an efficient, and let me end by giving you a simple example. For example, let us look at a Morse code, okay, one of the earliest and most popular codes, source codes for the English alphabet, used in the, of course, everyone must be familiar with the Morse code, which is used in the telegraph, and one of the most popular source codes for English alphabet, and this is nothing but a source code, correct, one of the most popular and if you look at the Morse code, instead of zeros and ones you have two kinds of symbols. You can think of them as zeros and ones. You have a dot and you have a dash, okay, rather than use. So, you have a dot, so you have a 2-bit, so you have a binary code. So, you have a binary code, so you have dots and dashes. So, Morse code can be thought of as a binary code, where each binary code corresponding to the English alphabet and of course the numbers, right. So, each alphabet and each number is represented by using a series of sequence of dots and dashes, and you will see that in the Morse code the length of a code word is roughly, of course the Morse code was derived more than 100 years ago, before information theory was in practice. Length of the code word is roughly, okay, let us say approximately, and one of the reasons Morse code is very efficient is inversely proportional to the frequency, correct, to the natural frequency of particular symbol. For example, if you can look at the symbol T, this is represented using dash, okay, you can think of this as a 1 bit, because T occurs rather frequently in the English alphabet. Several alphabets use T, for instance. In fact, the word the uses as T. So many words. So, the word T occurs rather frequently, and therefore, it has a very compact representation, a single dash. Now, some of the alphabets which occur rather infrequently, for instance, the most common one that you can think of is the alphabet Q. If you look at Q, Q therefore has this longer representation, that is dash, dash, dot, dash. So, this is occurs infrequently, implies longer code word, okay. In fact, if we look at Z, that is also which also occurs infrequently, that is dash dash dot dot, again occurs infrequently, therefore it has a longer code. This is occurs, T occurs frequently. Implies shorter code word. Okay. So, that is the basic idea. So, even a code like the Morse code, which was derived, which was of course established, which was designed hundreds of years ago for, and which in fact formed the backbone of the telegraphy system, was in fact based on this principle much before, of course, the principles of information theory were formalized, that longer which if you think about it is also intuitive, that is more frequently occurring symbols have to be represented by code words having smaller lengths, right, and the less frequently, that is the rather infrequent symbols can be represented using code words which have possibly longer lengths, and that is how one designs an efficient code, and that same is verified by the optimization framework that we have derived, and the solution to the optimization problem for minimizing the average code word length, where we have shown that to the lowest average code word length is achieved using code word length Li, which is in fact log, which is given as the log to the base 2 1 over pi. Of course, we have showed that using a constrained optimization framework, all right, using the KKT framework, formulating the Lagrangian, using a Lagrangian multiplier, Lagrange multiplier, solving this, right, solving the Lagrangian to obtain the optimal code word length Li, which is given by log to the base 2 1 over pi. All right. So, we will stop here, and in the subsequent modules we will look at schemes to design efficient codes in order to achieve this lower bound. All right. Thank you very much.